There we go. There we go. Cool. All right. Welcome to segment number 2 of Optics Academy. Today we are talking about lenses. So lenses, what do we know about lenses? I'm sure all of you know these. They refract light, so they go through and bends light. They're typically made spherical, and that's actually because it's a much easier geometry to handle. And they are pretty close to what we want them to be. You'll see shortly. Yeah, anyway. So, okay. How do we get to modeling a lens? So we just mentioned they're spherical, right? This means that each surface of the lens is spherical. So here we're zooming in on a single spherical surface. So this is one medium, and M stands for medium, and then NL stands for lens. We're just imagine we're like zooming in a lot, and like this is all a lens, or you have a really thick lens or something. So essentially what happens is if you looked into lenses, you might recognize this. This is a Gaussian formula for a single surface. So NM is this medium, NL is this medium, the refractive index, right? And then R1 here, R stands for radius of curvature. So because we mentioned the surface is spherical, right? So if you were to extend the surface into an entire circle here, that is not a circle, but an entire circle, the radius of that circle is the radius of curvature, and that's R. It's a good descriptor for the curvature of our lens, right? And then SO and SI are just the, SO is actually a variable because you can choose to place your object whatever distance from your surface, your imaging surface, right? And depending on this, your image distance is going to change, because you can see that there's like 5 variables. So if you had 4 of them, you can figure out the 5th one. How does this work? There's actually a very simple derivation for it. Can anyone see it? If not, it's okay. This is like high school math stuff. Any ideas? If not, it's okay. I'm not gonna throw everyone under the bus at 11:50 on a Sunday. But basically, ta-da, there's a triangle, right? And we know, okay, I should also mention that for SO, depending on where you place this, your incident angle is going to change, right? And essentially what's happening is in terms, okay. So last week, things we talked about law of reflection, law of refraction, and how light propagates in a straight path in a uniform medium, right? So in this case, there's some refraction going on, right? Right here. And okay, so this is essentially it. Here, you see how this is the normal to the surface here? We have the incident angle and the outgoing angle. Does this part look familiar? If you were here last week, or if you remember Snell's law or law of refraction. So knowing this fact, we just add some variables that describe, this length, which is again dependent on, like, not all of these are independent. So I'm not going to go through it here because it might take a few minutes too long. But essentially, all this comes from is just sine law and cosine law of is just trig, if you remember them. Sine law is like the ratio of the length to your angle, and then cosine is like when you have two lengths. When you have, let's say, 2 lengths sandwiching an angle, right? And you can basically work this out. So what are these? M is just an arbitrary thing describing this. This here we can call it the vertex. And you can think of it like, you know how like we call like the max or min the vertex of a parabola? In this case, the lens is not a parabola, but it's a spherical shape, and this is like the outermost point, or okay, you know what? Let's call it the point along the optical axis. So that's just called the vertex. The O for object, I for image, and C for center of curvature, right? Because we said this was R, radius of curvature. So C is your center of curvature. There's a lot of terminology, but I think this would be good to just wrap our heads around, like, for example, like how our inputs in Payload Designer actually work. Speaking of that, sign convention is something that's important as well. I might have like poked a couple of you guys about it, but essentially everything. Oh shoot. Yeah, essentially looking here, everything that is marked here for this surface is positive. So instead, if you had your object on this side or your image on this side, which is possible, we will get into that, they would be negative, if that makes sense. I feel like
Wait, so which values would be negative?
Okay, so let's say instead you had a prior lens or some other system that cast an image out here, and then that image feeds into this lens. It would mean that the object, so you had something before this that forms an image, let's say here, and that which then becomes the object for this lens, right? Because they're successive like that. So then that object would be to the right of your like surface, which would make it negative. On this side, it's positive. And the same goes for the image. If your image is on the to the right of your lens, or in this case your surface, then it's positive. If it's to the left, it becomes negative. And that is true if your lens was shaped or your surface was shaped the other way as well, like if it was concave instead. This still holds. It's just for lenses in general, we're going left to right. Your object is positive on the left, and your image is positive on the right, and then your radius of curvature here, if it curves this way, I don't know if I'm flipped or not. Okay, if it curves this way, okay, how I think of it is, if your curvature is shaped like a C and you're reading forwards, your curvature is positive. So this means that, let's say we had this, right? So we have two here, and pretend they're spherical. This does not look very spherical, but I didn't draw these from scratch this time because it was a little more work. But this one is like a C, so we have positive curvature here, and this one's like a backward C. So even though they're both convex, this is convex with a forward C, so it's positive. This is negative. And yeah, that's how R works. Sorry, wait. That's what the sign convention is for this R. And then for NI and NT, it might just be nice to know, just off the top of your head, that generally, like, your whatever lens or whatever material is going to have a higher N, higher refractive index. Light propagates slower, light bends away from the normal. Wait, nope. Light bends towards the normal, my bad, in your material than outside, because typically we're just kind of like air, right? In our case, for the Finch eye, the vacuum, yeah, that's this. And then, so for the thin lens, you guys have probably seen this on the Payload Designer SDD, but how we get this, again, any guesses? Oh wait, David, I see your question. I will get back to it. Okay, so essentially here what we had was a single surface, right? And this is the formula that gets us how how the image forms. If we knew the object distance and the curvature of the lens and the refractive indices, we can get the image distance. So in this case, that is information that we know as well. Like if we restricted this to just the left half of this, oh my gosh, I should annotate. If we restricted everything to just the left half of this, then that is what we just looked at, right? So essentially what we can do is just use that equation exactly. We have an M, we have an L, and then what we would get is, let's say an image that goes here. Then let's call this I prime. Oh no, this is called I prime. I1 prime. Okay, and then on the other side here, again, we have a system that looks like what we looked at before, right? So once again, but this time, notice that the image that we got from the previous system, which is now going to be our object for this one, is to the right of our surface. And all that means is that this distance, so we can call this SI prime 1 or something, is going to be negative. That's all that means. So then we just do our math with the previous formula. Yeah, we just use this. And then what we would be able to get if we simplified everything is this. So you can see SO would be the object distance for your first surface here. Your SI is your image distance that comes out of your second surface here. And what you would actually get is that for the stuff in the middle, they would just fall away in your derivations. And then we have NL and M that showed up in both, right? We've collected them together. R1, that corresponds to radius of curvature of this one, which in this case, like we mentioned, is positive because it looks like a C, and this one is negative. And what do we know? If you remember the simpler version of this formula, 1 over object distance plus 1 over image distance is equal to, can anyone tell me what this is? 1 over Any guesses? No guesses.
What if I guess R and I don't really know if I'm right or what that sounds?
Okay, thank you for the guess. It is not R. But that narrows down our options, right? Okay. I guess an F in the chat because it is actually F. Okay. So this is our focal length for the system, for the lens. Yeah, we don't really speak of focal lengths when it comes to the when it comes to this, but oh yeah, this was just the derivation that I was talking about. Whoops. Yeah, let's say first image forms here, feeds into the second surface, and then you get this. But yeah, this is one of our focal lengths. So this, oh shit, I am so bad with Zoom, guys. Wait. So this here is the simplified Gaussian equation that is also in our SCD. And yeah, okay. Okay. These are also in the SCD, but we figured we could talk about these here. So because in the Finch eye, we have both the collimator and the focuser. And they are actually just use cases of like a lens. Like you could think of it as a thin lens in this case, because we're staying to like simple cases. But essentially, a collimator is a lens. It could be, it doesn't have to be a lens, but in this case, let's say a lens that takes input light and then outputs it as parallel rays, right? As collimated light. So how do we do this? Let's go back. Let's go back to this. We said that all of this was just 1 over f, so that's what we'll just think of it as. So here, when we have our output rays collimated, so let's say you have your input like this. Oh no, okay, and then your output rays are like are very much in parallel. Pretend that's in parallel. What information does that give us relevant to this equation? The fact that light rays are in parallel. We're looking at the output here. Hint. Yeah, go for it.
Does SI go to infinity maybe?
SI or SO? SI.
O is on the left side, right?
No,
Is
you're
the
right.
object distance?
SI. Yep. So SI is our image distance, right? So you can picture it as, shoot, I don't have a GIF right now, but how can we do this? Okay, so let's say we had some input here where our image formed here. Then this is our SI, right? And our beams are very much not parallel. But let's say we had some other input such that our beams formed over here. Then our image formed over here. Then you see how the rays go further out. And let's say it was out here. Then if you move this point for your image to infinity, then you actually get parallel light. That makes sense, right? So then if we let this go to infinity, what happens? 1 over SO plus 1 over infinity, we're gonna just go to 0, right? Is we said that this whole right-hand part was 1 over F. So what does this give us? SO is equal to F. Ta-da! So this means that if you put any object at the focal length of the lens, what you get is collimated light. Does that make sense? So
I said very cool.
Okay, so yeah, so our other use case is sorry. Okay, our other use case is the focuser. But some of you might notice that this is essentially this, but just like flipped, right? So you can probably guess how this would apply then. We would do the exact same thing, just with SO instead, right? Because we know that our input rays are collimated. So if you put infinity as your object distance, then what you end up with is this goes to 0, and your image distance is equal to your focal length, because 1 over SI equals 1 over F. So what does this tell us here? If you have parallel rays as input, then your image forms at a focal distance from your lens. Okay, wait, I need to speed. I was gonna say, what does this mean for like our payload, right? So for our 4 optics, because we are super high up, we can think of the object's distance as infinity, right? It's 500 kilometers. We are tiny. So this means that collimated light is going in, and our image is going to form at a distance of a focal distance from, well, instead of like a single lens, because our 4 optics is complicated, we're just going to say the principal plane, which represents it as like a single, like a more simple system. And that's why we put our slit at a focal distance, in the focal plane, I guess, at a focal distance from the location of the plane that would represent the 4 optics as a simpler system. Yes, okay. Yeah, and also the collimator and the focuser that we have in our system, if you look at those, you can work out like how this fits with, you know, for example, our component spacing, that like stuff you worked on, and like yeah, essentially that was that. So what are the assumptions we made? Paraxial approximation. What does this mean? Par means, I don't know what par means, but it means close. Axial is just the axis, right? So this is our optical axis. So it goes through the center of the lens. This, right? So what this means is that so long as your rays are close enough to this axis, we can use this equation. Have you seen it? I don't know, maybe like physics or like, I don't know, any math class, that like sine, like your small angle approximation. Sine theta is approximately theta when theta is small. Tan theta is approximately theta when theta is small. We didn't go through this, but if we were to have worked through these derivations with the triangles, Civ 102, Civ 102, what? Okay, sure. Then yeah, we will have worked on assumptions that, for example, phi is small, then certain things fall away, like the signs and whatever. And so that's what paraxial means. And it's very useful in geometric optics because it just makes things a lot simpler. And typically with lenses, like it's a pretty good approximation. And then things must have changed after Collins left. But Alan must have been amazing though. He taught you guys things. Sign convention, which I already mentioned. Just make sure to keep them straight, because if not, you end up with things like random things going to zero. Because here we know sanity check. For example, this is 1/f, right? And let's say we have a positive focal length here, because it's a, we will get into this more later, but for this lens, because of the concave, we'll have a positive focal length. So this means that we want this to be positive, right? We said NL is a higher refractive index than like air or vacuum or whatever. So that means this part is positive. That means this part must also be positive. But you can imagine that like we can have random R1 and R2, right? So long as they're convex, this should be positive, but that makes sense because if R1 is positive, R1 is positive, R2 is negative because it's backwards, then this becomes positive, right? If you flip things, it would go all wonky. So like stuff to keep in mind for Paleo Designer. That is it. I'll cut it there. Questions though?
What other
wait,
types of
David.
lens geometries are there?
Yes. Okay. So I didn't put in screenshot, but nope. Okay, so we have like concave convex, right? But we can also have like a flat surface. We can have, I don't know, let's see. Oh, sure, this is pretty good. So okay, so this is convex surface on both sides. Oh wait. Why is this so small? No. Okay, we'll just go here. This is a plano-convex lens because a single side is flat, the other side is curved outwards. This here is a, what do we call this again? Because it's like convex on one side and concave on the other side, and it looks sort of like a contact lens. I forget what it's called. Yeah, sorry. We'll get back to you on that. And this one is concave very clearly. This is a plano-concave lens. And this one is similar to this. Oh, no. Okay. So this one is actually also a convex lens, and this is also a concave lens, but then there will be subcategories. I can't remember the specific name, but how do we know this is convex? What does this have in similarity with this one? It is fatter in the middle than the edges. So that's what makes it a convex lens. So it will have a positive focal length. If you remember from all my ramblings. This one is concave, and so is this one because it has like a narrower waist than the edges. Those are like the shapes of lenses. But I think David was referring to, I think when he asked this question was when I was talking spherical. So you can have spherical surfaces for these, any of these curved ones. You can also have, I mean, parabolic, I guess. I don't think anyone makes parabolic lenses, but hyperbolic is actually the geometry that would make things perfect. So for all of these equations that we looked at here, like a hyperbolic surface would actually work perfectly, but they are harder to make, like manufacturing wise. So we just use spherical. And also, if you zoom in, oh, I don't have an image of this. But essentially, if you think about, because okay, we call this the vertex, right? If you think about a sideways parabola, a sideways arc on a circle, and also a sideways hyperbola, if you zoom in close enough to the vertex, like imagine they're all overlapping, the three look very similar. Does that make sense? Like if we zoom in close enough, I can try to draw this, but it won't work. But let's say your parabola looks like this. Oh shit, okay. Let's say it looks like this, and let's say your hyperbola looks like this. Oh my god. But essentially if you zoom in really close on this, like the three are pretty much overlapping, and that is in line with our approximation of, the rays are pretty close to the axis, like as in this angle is small. So then you can see how this is a pretty good approximation. So that's why we're just like, okay, you know what, we're gonna do spherical because it's like a lot more feasible. When we talk about aberrations, this will come back again. But yeah, that was that question. Anything else? I guess I can answer one more question if there's anything, and then we'll move into the meeting because we're over time. Okay, if not, I'm gonna stop the recording here.